The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
In today's lecture, I want to develop several more formulas that will allow us to reach our goal of differentiating everything. So these are derivative formulas. And they come in two flavors. The first kind is specific. So some specific function we're giving the derivative of, and that would be, for example, x to the n or 1 over x. Those are the ones that we did a couple of lectures ago. And then there are general formulas. And the general ones don't actually give you a formula for a specific function, but tell you something like if you take two functions and add them together, their derivative is the sum of the derivatives. Or if you multiply by a constant, for example, so c times u, the derivative of that is c times u prime, where c is constant. All right, so these kinds of formulas are very useful, both the specific and the general kind. For example, they're needed, so we need both kinds for polynomials. And more generally, pretty much any set of formulas that we give you will give you a few functions to start out with, and then you'll be able to generate lots more by these general formulas. So today, we want to concentrate on the trig functions. And so we have we'll start out with some specific formulas. And they're going to be the formulas for the derivative of the sine function and the cosine function. So that's what we'll spend the first part of the lecture on. And at the same time, I hope to get you very used to dealing with trig functions, although that's something that you should think of as a gradual process. All right, so in order to calculate these, I'm going to start over here and just start the calculation. So here we go. Let's check what happens with the sine function. So I take sine x plus delta x. I subtract sine x. And I divide by, sorry, let's leave a little space there, sine x and divide by delta x. All right, so this is the difference quotient. And eventually, I'm going to have to take the limit as delta x goes to 0. And there's really only one thing we can do with this to simplify it or change it, and that is to use the sum formula for the sine function. So that's this. That's sine x cosine delta x plus oh, that's not what it is, huh? Okay. So what is it? Sine x, sine delta x. Okay, good, you remember. Plus cosine. No? Oh, okay. So which is it? Okay. All right, let's take a vote. Is it sine sine or is it sine cosine? Okay. So is this going to be cosine? All right. All right, you better remember these formulas, all right? Okay, it turns out that it's sine cosine. All right, cosine sine. So here we go. No, you got to do x here, sine delta x. All right? So now, there's lots of places to get confused here. And you're going to need to make sure that you get it right. All right? So we're going to put those in parentheses here. Sine a plus b is sine a cos b plus cos a sine b. All right? Now that's what I did over here, except it was the letter x was a, and the letter b was delta x. All right? Now that's just the first part. That's just this part of the expression. I still have to remember the minus sine x. That comes at the end, minus sine x. And then I have to remember the denominator, which is delta x. Okay? All right, so now, the next thing we're going to do is we're going to try to group the terms. And the difficulty with all such arguments is the following one. Any tricky limit is basically 0 over 0 when you set delta x equal to 0. If I set delta x equal to 0, this is sine x minus sine x, so it's a 0 over 0 term. Here we have various things which are 0 and various things which are non-zero. We must group the terms so that a 0 stays over a 0. Otherwise, we're going to have no hope. If we get some 1 over 0 term, we'll get something meaningless in the limit. So I claim that the right thing to do here is to notice, and I'll just point out this one thing, is that when delta x goes to 0, this cosine of 0 is 1. So it doesn't cancel unless we throw in this extra sign term here. So I'm going to use this common factor and combine those terms. So this is really the only thing that you're going to have to check in this particular calculation. So we have the common factor of sine x, and then that multiplies something that will cancel, which is cosine delta x minus 1 divided by delta x. So that's the first term. And now what's left? Well, there's a cosine x that factors out, and then the other factor is sine delta x over delta x. Okay, now, does anyone remember from last time what this thing goes to? How many people say 1? How many people say 0? All right, it's 0. That's my favorite number. All right, 0. It's the easiest number to deal with. So this goes to 0, and that's what happens as delta x tends to 0. Now how about this one? This one goes to 1, my second favorite number, almost as easy to deal with as 0. And these things are picked for a reason. They're the simplest numbers to deal with. So altogether, this thing, as delta x goes to 0, goes to what? I want a single person to answer, a brave volunteer. All right, right back there. Cosine. Because this factor is 0, it cancels, and this factor has a 1, so it's cosine. So it's cosine x. All right, so our conclusion over here, I'll put it in orange, is that the derivative of the sine is the cosine. All right? Okay, now I still want to label these very important limit facts here. This one we'll call A, and this one we're going to call B, because we haven't checked them yet. I promised you I would do that, and I'll have to do that this time. So we're relying on those things being true. Now I'm going to do the same thing with the cosine function, except in order to do it, I'm going to have to remember the sum rule for cosine. So we're going to do almost the same calculation here. We're going to see that that will work out. But now you have to remember that cosine of A plus B is equal to cosine cosine. No, it's not cosine squared, because there are two different quantities here. It's cosine A cosine B minus, here's the minus sign, sine A sine B. All right. So you'll have to be willing to call those forth at will right now. So okay, so let's do the cosine now. So that's cosine x plus delta x minus cosine x divided by delta x. Okay, there's the difference quotient for the cosine function. And now I'm going to do the same thing I did before, except I'm going to apply the second rule, that is the sum rule for cosine. And that's going to give me cosine x cosine delta x minus sine x sine delta x. And then I have to remember, again, to subtract the cosine divided by this delta x. And now I'm going to regroup just the way I did before. And I get the common factor of cosine multiplying cosine delta x minus 1 divided by delta x. And here I get the sine x, but actually it's minus sine x. And then I have sine delta x divided by delta x. All right? The only difference is this minus sign, which I stuck inside there. Well, that's not the only difference, but it's a crucial difference. OK, again, by a, we get that this is 0 as delta x tends to 0, and this is 1. Those are the properties I called a and b. And so the result here, as delta x tends to 0, is that we get negative sine x. That's the factor, negative sine x. All right, so this guy is negative sine x. And I'll put a little box around that too. All right, now these formulas take a little bit of getting used to, and but before I do that, I'm going to explain to you the proofs of a and b. All right, so we'll get ourselves started by mentioning that. Now, maybe before I do that, though, I want to show you how a and b fit into the proofs of these theorems. So let me just make some remarks here. So this is just a remark, but it's meant to help you to frame how these proofs worked. So first of all, I want to point out that if you take the rate of change of sine x, now let's start with cosine, because it's actually a little bit less obvious. If I take the rate of change of cosine x, so in other words, this derivative, at x equals 0, then by definition, this is a certain limit as delta x goes to 0. So which one is it? Well, I have to evaluate cosine at 0 plus delta x, but that's just delta x. And I have to subtract cosine at 0, that's the base point, but that's just 1. And then I have to divide by delta x. And lo and behold, you can see that this is exactly the limit that we had over there. This is the one that we know is 0 by what we call property A. And similarly, if I take the derivative of sine x at x equals 0, then that's going to be the limit as delta x goes to 0 of sine delta x over delta x. And that's because I should be subtracting sine of 0, but sine of 0 is 0. All right? So this is going to be 1 by our property b. And so the remark that I want to make, in addition to this, is something about the structure of these two proofs, which is the derivatives of sine and cosine at x equals 0 give all values of d by dx sine x, d by dx cosine x. So that's really what this argument is showing us, is that we just need one rate of change at one place, and then we work out all the rest of them. All right, so that's really the substance of this proof. That, of course, really then shows that it boils down to showing what this rate of change is in these two cases, and a equals. So now there's enough suspense that we want to make sure that we know that those answers are correct. All right, I think Looks like the erasers are over here. Okay, so let's demonstrate both of them. I'll start with B. So I need to figure out property B. Now, we only have one alternative as to a type of proof that we can give of this kind of result. And that's because we only have one way of describing sine and cosine functions. That is geometrically. So we have to give a geometric proof. And to write down a geometric proof, we're going to have to draw a picture. And the first step in the proof really is to replace this variable delta x, which is going to 0, with another name which is suggestive of what we're going to do, which is the letter theta for an angle. Okay, so let's draw a picture of what it is that we're going to do. Now, here's the circle, and here is the origin, and here's some little angle. Well, I'll draw it a little larger so that it's visible. Here's theta, all right? And this is the unit circle. I won't write that down on here, but that's the unit circle. And now sine theta is this vertical distance here. Maybe I'll draw it in a different color so that we can see it all. Okay, so here's this distance. So this distance is sine theta. Okay? Now, almost the only other thing we have to write down in this picture to have it work out is that we have to recognize that when theta is the angle, that's also the arc length of this piece of the circle when measured in radians. So this length here is also arc length theta, that little piece in there. So maybe I'll use a different color for that to indicate it. So there's orange, and that's this little chunk there. Okay? So those are the two pieces. Now, in order to persuade you now that the limit is what it's supposed to be, I'm going to extend the picture just a little bit. I'm going to double it just for my own linguistic sake and so that I can tell you a story, all right, so that you'll remember this. So I'm going to take a theta angle below, and I'll have another copy of sine theta down here. And now the total picture is really like a bow and its bowstring there, all right? So what we have here is a length of 2 sine theta, so maybe I'll write it this way, 2 sine theta. I just doubled it, and here I have underneath 2, whoops, I got it backwards. Sorry about that. Trying to be fancy with the colored chalk, and I have it reversed here. So this is not 2 sine theta. 2 sine theta is the vertical. That's the green. So let's try that again. This is 2 sine theta. All right. And then in the denominator, I have the arc length, which is theta is the first half, and so double it is 2 theta. All right. So if you like, this is the bow, and up here we have the bowstring. All right. And of course, we can cancel the 2's. That's equal to sine theta divided by theta. And so now why does this tend to 1 as theta goes to 0? Well, it's because as the angle theta gets very small, this curved piece looks more and more like a straight one. All right? And if you get very, very close here, the green segment and the orange segment would just merge. They would be practically on top of each other. And they have closer and closer and closer to the same length. So that's why this is true. I guess I'll articulate that by saying that short curves are nearly straight. All right, so that's the principle that we're using, or short pieces of curves, if you like, are nearly straight. So if you like, this is the principle. So short pieces of curves. All right, so now I also need to give you a proof of A. And that has to do with this cosine function here. This is the property A. And so I'm going to do this by flipping it around, because it turns out that this numerator is a negative number. If I want to interpret it as a length, I'm going to want a positive quantity. So I'm going to write down 1 minus cosine theta here, and then I'm going to divide by theta there. All right? Again, I'm going to make some kind of interpretation. Now, this time, I'm going to draw the same sort of bow and arrow arrangement, but maybe I'll exaggerate it a little bit. So here's the vertex of the sector, but we'll maybe make it a little longer. All right. All right, so here it is. And here was that middle line, which was the unit. Whoops. Okay, I think I'm going to have to tilt it up. Okay, let's try from here. All right. Well, you know, on your pencil and paper, it'll look better than it does on my blackboard. Okay, so here we are. Here's this shape. Now, this angle is supposed to be theta, and this angle is another theta. So here we have a length, which is again theta, and another length, which is theta over here. That's the same as in the other picture, except we've exaggerated it here. And now we have this vertical line, which again I'm going to draw in green, the bowstring. But notice that as the vertex gets farther and farther away, the curved line gets closer and closer to being a vertical line. That's sort of the flip side by expansion of the zoom-in principle, the principle that curves are nearly straight when you zoom in. If you zoom out, that would mean sending this vertex way, way out somewhere. The curved line, the piece of the circle, gets more and more straight. And now let me show you where this numerator, 1 minus cosine theta, is on this picture. So where is it? It's, well, this whole distance is 1, but the distance from the vertex to the green is cosine of theta, right? Because this is theta, so dropping down the perpendicular, this distance down back to the origin is cosine theta. So this little tiny bitty segment here, which is basically the gap between the curve and the vertical segment. So the gap is equal to 1 minus cosine theta. All right? And so now you can see that as this point gets farther away, if this got sent off to the status center, you would hardly be able to tell the difference. The bowstring would coincide with the bow, and this little gap between the bowstring and the bow would be tending to 0. And that's the statement that this tends to 0, as theta tends to 0. All right, the scaled version of that. Yeah, question down here.
The denominator also tend to 0, though?
The question is, doesn't the denominator also tend to 0? And the answer is yes. In my strange analogy here with zooming in, what I did was I zoomed out the picture. So in other words, if you imagine, imagine you're taking this and you're putting it under a microscope over here, and you're looking at something where theta is getting smaller and smaller and smaller and smaller. All right? But now, because I want my picture, I expanded my picture. So the ratio is the thing that's preserved. So if I make it so that this gap is tiny, yeah, let me say this one more time. I'm afraid I've made life complicated for myself. If I simply let this theta tend into 0, that would be the same effect as making this closer and closer in, and then the vertical would approach. But I want to keep on blowing up the picture so that I can see the difference between the vertical and the curve. So that's very much like if you're on a video screen and you zoom in, zoom in, zoom in, zoom in. So the question is, what would that look like? That has the same effect as sending this point out farther and farther in that direction, to the left. And so I'm just trying to visualize it for you by leaving the theta at this scale, but actually the scale of the picture is then changing when I do that. So both theta is going to 0, but I'm rescaling it so that it's of a size that we can look at it. And then imagining what's happening to it. Okay? Does that answer your question?
My question then is, that seems to prove that that limit is equal to 0 over 0.
It proves more than it's equal to 0 over 0. It's the ratio of this little short thing to this longer thing. And this is getting much, much shorter than this total length. You're absolutely right that we're comparing two quantities which are going to 0, but one of them is much smaller than the other. In the other case, we compared two quantities which were both going to 0, and they both end up being about equal in length. But here, the previous one was this green line. Here it's this little tiny bit here, and it's way shorter than the 2 theta distance. All right? Or theta. Yeah, another question.
Cos theta minus 1 over cos theta is the same as 1 minus cos theta over theta?
Cos theta minus 1 over...
The equation that you wrote beside me right here.
So here, what I wrote is cosine delta x minus 1 divided by delta x. Okay? And I claim that it goes to 0. Here, I wrote the minus that. That is cosine theta. I replaced theta by delta x by theta, but then I wrote this thing. So cosine minus theta minus 1 is the negative of this. All right? And if I show that this goes to 0, it's the same as showing the other one goes to 0. Another question. So the question is, what about this business about arc length? So the word arc length, that shape, that orange shape is an arc. And we're just talking about the length of that arc, and so we're calling it arc length. That's what the word arc length means. It just means the length of the arc. Why is this length theta? Okay, so this is a very important point, and in fact, it's the very next point that I wanted to make. Namely, notice that in this calculation, it was very important that we used length. And that means that the way that we're measuring theta is in what are known as radians. All right? So that applies to both B and A. It's a scaled change in A and doesn't really matter, but in B it's very important. The only way that this orange length is comparable to this green length, the vertical is comparable to the arc, is if we measure them in terms of the same notion of length. If we measured them in degrees, for example, it would be completely wrong. We divide up the angles into 360 degrees, and that's the wrong unit of measure. The correct measure is the length along the unit circle, which is what radians are. And so this is only true here if we use radians. All right? So again, a little warning here that this is in radians. So now here x is in radians. And the formulas are just wrong if you use other units. Yeah. Okay, so the second question is, why is this crazy length here 1? And the reason is that what I did was, the relationship between this picture up here and this picture down here is that I'm drawing a different shape. Namely, what I'm really imagining here is a much, much smaller theta, okay? And then I'm blowing that up in scale. So this scale of this picture down here is very different from the scale of the picture up there. And if the angle is very, very, very small, then 1 has to be very, very long in order for me to finish the circle. So in other words, this length is 1 because that's what I'm insisting on. So I'm claiming that that's how I defined this circle, to be of unit radius. Another question.
For part A, there was a unit proof. Wouldn't it be that I'm having a little difficulty conceptualizing it because it seems to me that as theta gets smaller and smaller, the ratio between 1 minus cosine theta and theta will get closer and closer to 1. Like, I don't understand how that is to 0 exactly.
Okay, so the question is, it's hard to visualize this fact here. Okay, so let me take you through a couple of steps, all right? Because I think probably other people are also having trouble with this visualization. The first part of the visualization I'm going to try to demonstrate on this picture up here. The first part of the visualization is that I should think of the beak of a bird closing down, getting narrower and narrower. So in other words, theta has to be getting, the angle theta has to be getting smaller and smaller and smaller. Okay, that's the first step. So that's the process that we're talking about. Now, in order to draw that, once theta gets incredibly narrow, in order to depict that, I have to blow the whole picture back up in order to be able to see it. Otherwise, it just disappears on me. In fact, in the limit, theta equals 0, it's meaningless. It's just a flat line. That's the whole problem with these tricky limits, is they're meaningless right at the 0, 0 level. It's only just a little away that they're actually useful, that you get useful geometric information out of them. So we're just a little away. So that's what this picture down below in part A is meant to be. It's supposed to be that theta is open a tiny crack, just a little bit. And the smallest I can draw it on the board where you can visualize it is using the whole length of the blackboard here for that. So I've opened a little tiny bit, and by the time we get to the other end of the blackboard, of course, it's fairly wide. But this angle theta is a very narrow, is a very small angle. All right, so I'm trying to imagine what happens as this collapses. Okay? Now, when I imagine that, I have to imagine a geometric interpretation of both the numerator and the denominator of this quantity here. And just see what happens. Now, I claim the numerator is this little tiny bit over here. And the denominator is actually, it's half of this whole length here, but a factor of 2 doesn't matter when you're seeing whether something tends to 0 or not. All right? And I claim if you stare at this, it's clear that this is much shorter than that vertical curve there. And I'm claiming, so this is what you have to imagine, is that as it gets smaller and smaller and smaller still, that has the same effect of this thing going way, way, way farther away, and this vertical curve getting closer and closer and closer to the green. And so that the gap between them gets tiny and goes to 0. All right? So not only does it go to 0, that's not enough for us, but it also goes to 0 faster than this theta goes to 0. And that's what's over. I hope the evidence is pretty strong here because it's so tiny already at this stage. All right. We are going to move forward. And you'll have to ponder these things some other time. So I'm going to give you an even harder thing to visualize now, so be prepared. Okay? Okay. So now, the next thing that I'd like to do is to give you a second proof, because it really is important, I think, to understand this particular fact more thoroughly, and also to get a lot of practice with sines and cosines. So I'm going to give you a geometric proof proof of the formula for sine here, for the derivative of sine. So here we go. This is a geometric proof of this fact. This is for all theta. All right, so far we only did it for theta equals 0. And now we're going to do it for all theta. So this is a different proof, but it uses exactly the same principles. All right? So I want to do this by drawing another picture. And the picture is going to describe y, which is sine theta, which is the, if you like, the vertical position of some circular motion. So I'm imagining that something is going around in a circle. All right, some particle is going around in a circle. And so here's the circle, here's the origin, this is the unit distance, and right now it happens to be at this location P. All right, maybe we'll put P a little over here. And here's the angle theta. All right, and now we're going to move it. We're going to vary theta, and we're interested in the rate of change of y. So y is the height of P, but we're going to move it to another location. We'll move it along the circle to Q. All right, so here it is. Here's the thing. So how far did we move it? Well, we moved it by an angle delta theta. All right, so we started theta. Theta is going to be fixed in this argument, and we're going to move a little bit delta theta. And now we're just going to try to figure out how far the thing moved. Well, in order to do that, we've got to keep track of the height, the vertical displacement here. So we're going to draw this right angle here, and this is the position R, and then this distance here is the change in y. All right, so the picture is we have something moving around a unit circle, a point moving around a unit circle. It starts at P, it moves to Q. It moves from angle theta to angle theta plus delta theta. And the issue is, how much does y move? And the formula for y is sine theta, so that's telling us the rate of change of sine theta. All right, well, so let's just try to think a little bit about what this is. So first of all, I've already said this, I'm going to repeat it here. Delta y is PR. It's going from P and going straight up to R. That's how far y moves. That's the change in y. That's what I said up in the right-hand corner there. Oops, I said PR, but I wrote PQ, huh? All right, that's not a good idea. All right, so delta y is PR. And now I want to draw the diagram again one time. So here's Q, here's R, and here's P. And here's my triangle. And now what I'd like to do is draw this curve here, which is the piece of the arc of the circle. But really, what I want to keep in mind is something that I did also in all these other arguments, which is, maybe I should have called this orange, but I'm going to think of this straight line between. So it's the straight line approximation to the curve that we're always interested in. So the straight line is much simpler because then we just have a triangle here, and in fact, it's a right triangle. Right? So we have the geometry of a right triangle, which is going to now let us do all of our calculations. Okay, so now the key step is this same principle that we already used, which is that short pieces of curves are nearly straight. So that means that this piece of the circular arc here from P to Q is practically the same as the straight segment from P to Q. All right, so that's this principle that well, let's put it over here, is that PQ is practically the same as the straight segment from P to Q. So how are we going to use that? Well, we want to use that quantitatively in the following way. What we want to notice is that the distance from P to Q is approximately delta theta. Right? Because the arc length along that curve, the length of the curve is delta theta, so the length of the green, which is PQ, is almost delta theta. So this is essentially delta theta, this distance here. Now, the second step, which is a little trickier, is that we have to work out what this angle is. So our goal, and I'm going to put it one step below because I'm going to put the geometric reasoning in between, is I need to figure out what the angle QPR is. If I can figure out what this angle is, then I'll be able to figure out what this vertical distance is, because I'll know the hypotenuse and I'll know the angle, so I'll be able to figure out what the side of the triangle is. So now, let me show you why that's possible to do. So in order to do that, first of all, I'm going to trade the boards and show you where the line PQ is. So the line PQ is here. That's the whole thing. And the key point about this line that I need you to realize is that it's practically perpendicular. It's almost perpendicular to this ray here. All right? It's not quite because the distance between P to Q is non-zero, so it isn't quite. But in the limit, it's going to be perpendicular. Exactly perpendicular, the tangent line to the circle. So the key thing that I'm going to use is that PQ is almost perpendicular to OP. All right? The ray from the origin is basically perpendicular to that green line. And then the second thing I'm going to use is something that's obvious, which is that PR is vertical. Okay? So those are the two pieces of geometry that I need to see. And now notice what's happening upstairs on the picture here in the upper right. What I have is the angle theta is the angle between the horizontal and OP. That's angle theta. If I rotate it by 90 degrees, the horizontal becomes vertical, it becomes PR, and the other thing rotated by 90 degrees becomes the green line. So the angle that I'm talking about, I get by taking this guy and rotating it by 90 degrees. It's the same angle. So that means that this angle here is essentially theta. That's what this angle is. Let me repeat that one more time. We started out with an angle that looks like this, which is the horizontal. That's the origin straight out horizontally. That's the thing that's labeled 1, that distance there. And then I also have that's my right arm, which is down here. My left arm is pointing up, and it's going from the origin to the point P. So here's the horizontal, and the angle between them is theta. And now what I claim is that if I rotate by 90 degrees up, like this, without changing anything, so that was what I did, the horizontal will become a vertical. That's PR, that's going up, PR. And if I rotate OP 90 degrees, that's exactly PQ. Okay? So let me even, well, I think I will draw it on there one time and see if you can, let's do it with some arrows here. So I started out with this, and then we'll label this as, let's see, Label this as orange. Okay, so red to orange. And then I rotate by 90 degrees. And the red becomes this, starting from P. And the orange rotates around 90 degrees and becomes this, this thing here. All right? So this angle here is the same as the other one, which I've just drawn. All right? Different origins for the, different vertices for the angles. Okay? Well, I didn't say that all arguments were supposed to be easy. All right, so I claim that the conclusion is that this angle is approximately theta. And now we can finish our calculation, because we have something with the hypotenuse being delta theta and the angle being theta. And so this segment here, PR, is approximately the hypotenuse length times the cosine of the angle. All right? And that is exactly what we wanted. If we divide by delta theta. We get delta y divided by delta theta is approximately cosine theta. All right? And that's the same thing as, so what we want in the limit is exactly the delta theta going to 0 of delta y over delta theta is equal to cosine theta. So we get an approximation on a scale that we can visualize, and in the limit, the formula is exact. Okay, so that is a geometric argument for the same result, namely that the derivative of sine is cosine. Yeah? You will have to do some kinds of geometric proofs sometimes. When you'll really need this is probably in 1802. So you'll need to make reasoning like this. This is, for example, the way that you actually develop the theory of arc length, and dealing with delta x's and delta y's is a common tool. All right, I have one more thing that I want to talk about today, which is some general rules. And so we took a little bit more time than I expected with this. So what I'm going to do is just tell you the rules, and we'll discuss them in a few days. So let me tell you the general rules. So these were the specific ones, and here are some general ones. So the first one is called the product rule. And what it says is that if you take the product of two functions and differentiate them, you get the derivative of one times the other plus the other times the derivative of the one. Now, the way that you should remember this, and the way that I'll carry out the proof, is that you should think of it as you change one at a time. And this is a very useful way of thinking about differentiation when you have things which depend on more than one function. So this is a general procedure. The second formula that I wanted to mention is called the quotient rule. And that says the following, that u divided by v prime has a formula as well. And the formula is u prime v minus uv prime divided by v squared. So this is our second formula. Let me just mention. And both of them are extremely valuable, and you'll use them all the time. This one, of course, only works when v is not 0. All right, so because we're out of time, we're not going to prove these today, but we will prove these next time, and you're definitely going to be responsible for these kinds of proofs.